Hello, today we will be introducing Fourier Transform Infrared Spectroscopy, FTIR. We will be addressing the basics with the infrared region, infrared spectroscopy, what is FTIR from practical standpoint and its analysis and sample preparation. This video will be divided into three sections: introduction, the infrared spectroscopy, Fourier transform infrared spectroscopy FTIR, sample and techniques. We hope by the end of this video you will have a better understanding of FTIR, when to use them and how. Section 1: Introduction to the infrared spectroscopy. What is infrared region? The infrared radiation lies between the visible and microwave portion of the electromagnetic spectrum. Infrared waves have a wavelength longer than visible and shorter than microwave and have frequencies that are lower than visible and higher than microwaves. The infrared region is divided into near, mid, and far infrared. Near infrared refers to the part of the infrared spectrum that is closest to visible light, and far infrared refers to the part that is closer to the microwave region. Mid-infrared is the region between these two. The primary source of infrared radiation is the thermal radiation. Heat is the radiation produced by the motion of atom and molecule in the object. The higher the temperature, the more the atom and molecule move and the more infrared radiation they produce. Any object radiates in the infrared. Even ice cube emits infrared. According to the principle of IR, molecular vibration takes place as a result of the observation of IR radiation when applied infrared frequency equal natural frequency of vibration. Every bound of functional group requires a different frequency for observation. Hence, characterized peak is observed for every functional group of part of the molecule. Infrared spectroscopy for isopropyl alcohol CH2OH is infrared observation bound. Identify the various functional group of the molecule. Section 2: Fourier Transform Infrared Spectroscopy FTIR. What is FTIR? FTIR stands for Fourier Transform Infrared, the preferred methods of infrared spectroscopy. In infrared spectroscopy, IR radiation is passed through a sample. Some of the infrared radiation is absorbed by the sample and some it's passed through. The resulting spectrum represented the molecular absorption and transmission. Create a molecular fingerprint of the sample. Like fingerprint, no two unique molecular structures produce the same infrared spectrum. This makes infrared spectroscopy useful for several types of analysis. So what information can FTIR provide? It can identify unknown materials. It can determine the quality or consistency of the sample. It can determine the amount of component in mixture. This booklet is an introduction to the concept behind FTIR spectroscopy. Superiority of FTIR. Dispersive infrared spectrometer suffer from several disadvantages insensitively. Speed and wavelength accuracy. Most of the light from the source does not in fact pass through the sample to the detector, but is lost in the narrowness of the focusing slides. Only poor sensitivity result. Since the spectrum takes minutes to record, the methods cannot be applied to fast process. Dispersive infrared spectrometers scan over the wavelength range and disperse the light by use of aggregating. These spectrometers suffer from wavelength inaccuracy associated with the backlash in the mechanical movement, such as the rotational of mirrors and grating, and internally different principle involved infrared transfer, infrared spectroscopy, which center of Michelson interferometer, so that the method can also be called interferometric infrared spectroscopy. Fourier transform infrared spectroscopy is preferred over dispersive or filtered method of infrared spectral analysis for several reasons. It is a non-destructive technique. It provides a basis measurement method that require no external calibration. It can increase speed, collecting scan every second. It can increase sensitivity. It has greater optical throughput. It's mechanically simple with only one moving part. Dispersive spectrometer. In order to measure an IR spectrum, the dispersion spectrometer takes several minutes. Also, the detector receives only a few percent of the energy of the original light source. Another that FTIR, in order to measure an IR spectrum, FTIR takes only a few seconds. Moreover, the detector receives up to 50 of the energy of the original light source, much larger than the dispersion spectrometer.
Theory of FTIR. Fourier transform infrared FTIR spectrometry was developed in order to overcome the limitation encountered with dispersive instruments. The main difficulty was the slow scanning process, a method for measuring all of the infrared frequencies simultaneously rather than individually was needed. A solution was developed that employed a very simple optical device called an interferometer. The interferometer produces a unique type of signal which has all of the infrared frequencies encoded into it. The signal can be measured very quickly, usually on the order of 1 second or so. Thus, the time element, being simple, is reduced to a matter of a few seconds rather than several minutes. Most interferometers employ a beam splitter which take the incoming infrared beam and divides it into two optical beams. One beam reflects off a flat mirror which is fixed in place. The other beam reflects off a flat mirror, which is one machine which allows this mirror to move a very short distance, typically a few millimeters, away from beam splitter. The two beams reflect of their respective mirrors and are recombined when they meet back at the beam splitter. Because the path that one beam travels is fixed length and the other is constantly changing as its mirror moves. The signal which exists, the interferometer, is the result of these two beams interfering with each other. The resulting signal is called an interferogram, which has the unique property that every data point a function of the moving mirror position, which makes up the signal, has information about every infrared frequency which comes from the source. This means that as the interferogram is measured, all frequencies are being measured simultaneously. The use of the interferometer result in extremely fast measurements. Because the analysis requires a frequency spectrum, a plot of the intensity at each individual frequency in order to make an identification. The measured interferogram signal cannot be interpreted directly. A means of decoding the individual frequencies is required. This can be accomplished via a well-known mathematical technique called the Fourier transformation. This transformation is performed by the computer, which then presents the user with the desired spectral information for analysis.